Hello everyone. In this video, I'm going to show you how to set up a new protocol on the BioTek H1 play reader. Also, for different reading modes, how to set up the parameters. So first you can do is here you can click like this task manager, right? You can create a new protocol. Or you can use read now, which basically it will now create a protocol directly, just do the experiment. So if you have something sort of on the fly, you can use this one. But if you have a routine things to do, for example, mirroring binding, mirroring, like nanobread assays, so on and so forth, it's better to create a protocol. So you just click create new. Okay. Once you click that, you will see this screen and double click procedure. Yeah, you will see a screen like this. Okay, let's just remove all these. Let's start over. So first, what you want to do is to choose your plate type. Okay, so BioTek actually has a lot of the different types of plates in here. Um, for a lot of applications, you can just choose the default 96 well or 384 well plate. But if you know exactly which one you're using, for example, if you're using a Corning low volume round bottom plate, you can choose this one specifically. The good thing for this is actually for different plates, you may have different so-called Z value, right? So because the depths of the each well, the wells for different plates could be different. So that will basically affect the optimal parameters in your measurements. So if you tell PlayReader exactly what kind of plate you're using, and it will give you the manufacturer default optimal parameters, it will be easier for you to further optimize it from there. But anyway, you can choose your plate. For example, we just use a 3D 96 watt plate. If you are generally for most of the assays we don't use lid. You can choose without lid. But if you are doing something with incubation, you probably want to put the lid on. Then you need to check this box. Okay. And there are a few other things, right? So for the you can choose also 384 well plate. This plate reader can only take either 96 or 384, or maybe, yeah, like even larger plates, but we seldom use that. There's another thing is called the Take 3 default, right? Take 3 is a special device we have. So basically you can put a 2 microliter of the solution, and then you can use that to measure the absorbance, fluorescence. So it's a very convenient way of dealing with very small volume samples. Okay, and so here also select wells. You can choose per step or at runtime, right? Per step will basically you define which wells to read in the protocol, or at runtime means actually what in this protocol you do not define which wells to read, but then when you run the protocol, will ask you, where are your samples, and you can select them. So generally we use this one for flexibility, but definitely if you have something, just like you keep doing exactly the same thing with the same play format, arrangement, and it's better to use this per step. Okay, read, right? So we have many different types of reading here. So for absorbance, let's take a look. So number one, remember absorbance is basically you're following a so-called Beer's law, right? And absorbance basically is a instrument independent parameter. That means absorbance measured on here, other like in our first floor lab, the UV spectrometer, you should get the same absorbance, right? As long as you have the same concentration of the solution, the same light path. So here you have different rate type, so-called endpoint. Basically, you just do single wavelength measurement. You can also do kinetics, which means you can do a time course reading. You can also do this so-called spectral scanning. That means you scan from one wavelength to another wavelength, right? So for endpoint, for example, here, if you just click here, endpoint, right? So you can choose your wavelengths you want. Basically, you just type in, for example, 400, and you can also select like more than one wavelength. You can do, say 500 here, right? And or you can do even more, right? So so basically you can do maximum 6 wavelengths for this single wavelength measurement. There's one option called wavelength switching per well. So what does it mean here, right? So if you check this, that means when you read well A1, for example, it will measure 450 first, then it will switch the wavelength to 500. Okay, still read in the same well. So that's useful when you have something, you want to measure both wavelengths, but it's also a kinetic measurement. You want to do a ratio between them, right? So you want to sort of try to minimize the difference between the two readings, right? The time difference between the two readings. You will do this wavelength switching per well. But there's a biggest disadvantage for this option is basically the reading is much slower because you have to keep switching the wavelengths. So generally, if it's a steady state measurement, we don't do this. Even for kinetic measurement, as long as the signal changes is not dramatic, I would say less than 5%. Generally, we'll just do without the wavelength switching. That will actually significantly make the reading process much faster. Okay, in terms of read speed, generally we choose normal. You can click edit, right? So what it does, it will for each data point, it will measure 8 times because we have this flash lamp. So it can do like 8 measurements in each well, right? And also after one reading, we will move to the next one, and then you know stop there for 100 milliseconds before the second run to avoid the signal crossover. But if you have something very fast, right, so fast kinetics, you probably want to go with this so-called sweep mode, right? And for this one, it doesn't have any delay after play movement, and also you only have one measurement per data point, right? So as you can imagine, it will be 8 times faster at least. Yep. So this is basically how you do this absorbance. There's a path length correction option here. If you check that, I mean, you can use this 977 nanometer as a test wavelength. I do not think our play reader is able to do this. I'm not quite sure because this is actually this requires a oh, maybe we can. Yeah, I don't know. So basically, this is a test wavelength is basically it's trying to use the water absorbance at that wavelength, right? Then you can calculate how how thick the or how deep the solution is, right? So the light path, basically. However, the thing is, if you use the exact same volume for all the wells, you don't really need to use this path length correction options, right? This is mostly useful when you have like different volumes in different wells, which is not our case I would say 99.9% of applications. So generally we just uncheck this, right? So then you can click OK. It will tell you, it will read absorbance here. Okay, and so let's take a look at the fluorescence options here. You can also click read. Oh, for absorbance, you can also do spectral scanning, right? So if you do spectral scanning, and you can click OK. So it will tell you here is that you can scan, from 300 to 700. You can also do this step. That means 10 nanometer each step means so the next one will be 310, 320, 330, so on and so forth, right? One thing you want to pay attention is for this kind of type of application, a lot of the plates we use, generally the microtiter plates, they are made out of polystyrene, right? So when you use polystyrene, generally the so-called absorbance cutoff is about like 300, I would say 300, to be safe, 350 nanometers. So if you have something below that wavelength, you'd better use a UV transparent plate, right? If you use polystyrene plate, it will start to become like opaque at that wavelength. So when you use this option, you want to be very careful, okay? Very careful about the plates you use. You can always just do a control experiment, right? So put water in that well and scan and see whether you can get reasonable background absorbance, okay? Um, and you can, for the same thing, you can change the read speed here, right? So we can add that. And then we can also take a look at fluorescence intensities, right? Fluorescence intensities is the same thing, right? You can do the endpoint, you can do spectral scanning, and also it will give you other optics options here. So let's first take a look at the monochromator options. So if you click OK, and just like absorbance, you can choose multiple wavelengths. You can choose up to 6, and say if you have 2 here, right, and you can change excitation, right? So you can use excitation for 85, 5 to 80. So that's more like a fizzy. You can also use like 405, and here is 480, like coumarin type of excitation. Okay, and for optics position, right? So here's the thing. So generally, to achieve the best sensitivity, you want to use the top position. So basically, the light, excitation light come into the well, and then your detector will be detecting over here, right? So it's just going through the top, and this is the best detection mode for homogeneous solutions. But if you have adherent cells, right? So basically cells attached on the bottom. For that type of application, the best way to do the measurement will be do the bottom, right? So basically light will come through the extract from the bottom, detect on the other end of the bottom, perpendicular to your excitation light. And the downside for that is that the excitation light and the emission light have to go through the plastic, right, which is the bottom of the well. That will attenuate your signal intensity. Um, for a lot of cases, if you're not sure, you can try both. But for a homogeneous solution, there's no point of trying bottom reading. But for adherent cells, you can always try both, right? For suspension cells, most likely the top reading will be sufficient. Okay, and gain is basically the electronic amplification for your signal, right? So you can change the gain, to any numbers, basically to maximize your reading. But the thing here is if you increase again, your electronic noise is going to increase too, right? So it won't increasing again will not increase your signal to noise. there's another thing is option, right? So options is it will basically try to help you to get automatic gain adjustment. So what it does is basically you can if so for example if you know A1 valve will give you the highest signal, right? Or you can just put a a known compound with the concentration comparable to your sample in there, and and you know that's gonna give you a high signal. You can just do automatic gain adjustment. It will do auto scale, right? And try to find the optimal gain for this. But generally, I think you can use this function just to do a pilot study to find the right gain value. But then I don't like to use it automatic gain for real measurements because I want to keep the gain value consistent, right? So basically, I generally for like reading for a real experiment, I'll just type in the gain value I need based on the automatic gain adjustment pilot study. Okay, and then for the same thing, you can do the wavelength switching per well as we described in the for the absorbance and read speed. Read height is another important parameter for fluorescence measurement, right? Unlike absorbance basically, you have the well here, light will go through the solution, go through the bottom of the well, right? So you measure the absorbance. But for fluorescence, it will just basically, go in here and then collect the other at the other like 90 degree, right? The other end. So then it's important to know the focal point, right, for this 90-degree angle. Uh, so this is basically why you need to adjust the read height. This is extremely important because this depends on the sample volume you have. For a lot of your applications, for example, if you have 200 microliter in the 96 well plate, probably you don't care too much about read height. It may give you a pretty large uh, like the tolerance basically, right? So maybe rate height 7 or rate height 9 millimeter will give you the same result. But if you have a smaller volume, for example, like 100 microliters in 96 well, you probably want to adjust that very carefully, right? That's another thing I mentioned when you choose a plate type. If you choose the correct brand and correct plate type, it will actually give you a optimal rate height value here. But anyway, you can also do this auto adjust just like you auto adjust again, right? So I would suggest for if you do this experiment for the first time, I will basically do the auto gain, auto adjust the height. And just try to get a feel of this the setting, right? So you can determine the optimal height at runtime, or you can just do it right in here, right in this program. You can choose a test well, right? For example, it's A1. You just click A1, and then start a calibration. It will basically go through all the probe height positions, and you are supposed to see, for example, distribution here, right? So like for example, like here, and the 6 millimeter height will give you the highest signal, and then you can just put that value in here. That's your best value for your experimental setup. This value mostly dependent on the volume of your solution in each well. Okay, you can do this, right? So you can click that. Uh, as you can see, when you add that, you can see this read is called F, right? It's called fluorescence. A means absorbance. You can also definitely do for fluorescence intensity, you can do filter based, right? So for monochromator based, the good thing is you can adjust any wavelengths you want, but the bad news is it has a limited so-called bandpass, right? Bandpass is for example, you have 500 nanometer set as an excitation light. If bandpass is 8 nanometer, that means you have light from 496 to 504 nanometer, right? So our monochromator bandpass is 8 nanometers. the same thing for the emission monochromator. But for filters, the good thing is you can have a super large bandpass, right? So you can even have 100 nanometers, or even use the long pass filter. You can collect all the light above 600 nanometers, something like that, right? So basically, filter-based measurement generally give you a more sensitive measurement. But the downside is that you have to make the filters, right? Which is basically make the assay. I mean, make. I mean, it's so basically you have to have a fixed fluorophore, and you know the wavelength emission, and then use a exactly matched filter, right? It's not as convenient as monochromator, but it's definitely a good function to have. So for example here, you can choose a filter set. We have multiple, filter set in our lab. So we have a list. You can go to Teams, instrument channel. You can see all the information here. And for example, if you just choose 340, so see this is I believe this is for the TR threads, right? So basically what you do is what you can see is 340 as adaptation, 30 is the bandpass, and 495 emission, 10 is the bandpass, right? And you can also select more than one, because our filter cube can have two sets of filters, and you can do here you can choose anything you want to use basically. And same thing, you can change again. You can also adjust the speed, height, and just as the monochromator stuff. Right? No, okay, yeah. Anyway, and then read. So that's basically for kinetics. Spectral scanning, it's the same thing as absorbance. You can do okay here. Yeah, so basically this is just like when you use a fluorometer, right?